Hello everyone. In this class, we will discuss sampling, an essential part in a digital communication systems where the source generates an analog signal, not a digital signal. So, when we have a source which generates analog signal, but we want to transmit using digital communication techniques, first we have to make the signal digital, and for doing that we need to convert the signal in some form where per second there will be a finite number of bits that will represent the signal. So, since in time an analog signal has infinite number of values, for every time instance there is a value, it is not possible to digitize a signal without first discretizing the time, and discretizing the time is called sampling. Later on we also have to discretize the amplitude, because any sample value, continuous sample value has infinite amount of information. So, we need to discretize the amplitude also, so that we can represent every sample by finite number of bits. That will be called quantization, and we will discuss it later. So, let us start sampling. So, we have a continuous time signal. So, we are going to discuss sampling. We have a continuous time signal which may look like this, and this is converted to a discrete time signal. So, we take at a regular interval, we take values like this, and we have a sequence of values. In between these sample values, there is no data in the signal. So, the time is discretized in this signal. So, if this signal is represented by x t, then this will be usually represented by x n, where this is 0, 1, 2, 3, 4 and so on, or sometimes x subscript n. So, this is discrete time signal. Now, when we discretize the signal, first we have to fix a gap between the samples. So, that is the sampling period. This is t. So, the sampling period we will denote it by T s, is denoted by T s, and then 1 by T s is called the sampling frequency. Which will be denoted by F s. So, in other words, we have, if we have a signal x t, after sampling we have a discrete time signal denoted by x n, which is nothing but x, this signal at n T s. Now, an important question here is whether we can recover this signal from the discretized signal, because we have removed all the values in between two consecutive samples. So, can we recover all the intermediate values, so that we can get back the original analog signal from the discrete time signal? That is an important question, and we will try to answer that question for some cases. In other words, when we discretize a signal, that is when we remove all the intermediate values between two samples, is there any loss of information? If there is no loss of information, in principle it should be possible to recover those values of the intermediate values from the samples we have. On the other hand, if there is some loss of information, that it is not possible to recover all the values from the samples. So, the question is it possible to recover the analog signal from the discrete time signal? We will answer that question for a special class of signals called band limited signal. So, what is a band limited signal? It is what we know basically as low pass or band pass signal. A band limited signal is so that the Fourier transform of the signal, which is denoted by x f, is 0 for all f which is greater than w or less than minus w, that is for all f whose absolute value is greater than w. So, what it means is, in the frequency domain, if you take minus w to plus w range, the Fourier transform of the signal is 0 outside this range. It is non-zero only in this range. So, it may be either a low pass signal or it may be a band pass signal like this, or a signal like this. So, this is band limited signal. Similarly, a stochastic process is also called band limited if the power density spectrum satisfies the same condition. So, a stochastic process is band limited if the power density spectrum is band limited. Okay. So, suppose we know that a signal is band limited in minus w to w range, then what is the rate at which we can sample, so that we can get back the original signal from the sample signal? That is, can we say that given that the signal is band limited in minus w to w, what is the minimum sampling frequency, so that even after sampling there is no loss of information? So, let us try to answer that question. Before we prove or we get an insight into why what rate is sufficient, let us first define what is called as Nyquist rate. The Nyquist rate for a band limited signal, band limited within minus w to w, is the sampling frequency f s equal to 2 w. So, 2 w is actually the bandwidth of the signal if it is low pass. So, then the sampling frequency is 2 times the maximum frequency. So, that is the Nyquist rate, 2 times the maximum frequency. And this Nyquist rate is the critical rate for sampling. In other words, if we sample a band limited signal above Nyquist rate, we can recover the original signal from the sample signal, and if it is below the Nyquist rate, we cannot recover the original signal from the sample signal. And we will try to first get an insight into why it should be true, and then we will also see how to actually recover the original signal if the sampling frequency is above the Nyquist rate. So, let us try to first get a feel of why Nyquist rate should be sufficient for recovery of the original signal in the frequency domain. Let us first see it in frequency domain. Suppose we have the signal x t whose spectrum is, whose spectrum magnitude is, so this is frequency, this is 0 frequency, this is w, this is minus W. So, this is the band limited spectrum of the band limited signal, and we want to sample it at some frequency. Now, the Nyquist rate is 2 times this, that is somewhere here, this is Fs, this is 2 times W, but we can sample it either at a lower rate than 2W or higher rate than 2W. So, let us first see what happens if we sample the signal at a higher rate than 2W. So, this is 2W, but we sample it at, let us say, here. Then what will be the discrete time Fourier transform of the sampled signal? We know that just like we have Fourier transform of continuous time signal, we have discrete time Fourier transform, which is abbreviated as DTFT of a sample signal or a discrete time signal. So, when we sample the signal xt, we get a discrete time signal, then we can take DTFT of that signal, and how will that DTFT look like? Given that the analog signal xt has this spectrum, this Fourier transform, it will look like this. First of all, DTFT will be periodic with period 2 pi. So, let us draw it here. So, this will be pi minus pi 2 pi 3 pi 4 pi and so on. So, the DTFT of the signal, that is, if the signal is denoted by xn and it has DTFT x j omega, then its magnitude will look like this. So, how will we get that? This W, this Fs will be mapped to 2 pi frequency and 0 will be mapped to here, and then the rest of the frequencies will be placed linearly accordingly. So, 2 pi is Fs, and so this will come here. So, this since Fs is greater than 2W, this W will be less than Fs by 2, which is somewhere here. Fs by 2 is somewhere here. So, and Fs by 2 will be mapped to pi. So, it will be like this. So, W frequency will be mapped to somewhere here, and then this same thing will repeat after shifting by multiples of 2 pi. So, this will be shifted to, this 0 will be shifted to 2 pi. So, we will get a copy of this here and at 4 pi here, then at minus 2 pi like this, then at minus 4 pi like this, and so on. So, this is the periodic DTFT of the sample signal. Now, as we can see in frequency domain, the DTFT of the signal has this spectrum as part of it. So, we can actually this whole spectrum is still present in this signal separately. There is no mix up of these different copies. So, we can still recover this signal, should be still possible to recover this signal from here, because we just take this part and do some processing and take this part and convert it to analog signal. So, we will see how to do it later, but we at least see that there is apparently no loss of information when we go from here to here. We get only multiple copies of this in disjoint frequency locations. On the other hand, if we sample the signal, original signal at a rate less than Nyquist rate, that is, if Fs is below 2W, what would we get? So, this is the case when Fs is greater than 2W. If Fs is equal to 2W, these two will touch at pi, even then it is recoverable. There is no mix up, what is called the aliasing, there is no aliasing. Now, let us see what will happen if Fs is less than 2W, that is Fs is somewhere here and Fs by 2 will be somewhere here less than W. In the same frequency scale, pi, 2 pi, 3 pi, 4 pi, minus pi, so this Fs by 2 now which is less than W will be mapped to pi. So, the copy of this here will look like this, because this Fs by 2 is mapped to pi. So, W will be mapped to something greater than pi, and then this will be shifted to 2 pi, the center 0 will shift to 2 pi, this whole thing, and then we will get something like this, and then it should also be shifted to 4 pi. So, we will get something like this, and then to minus 2 pi, something like this, and minus 4 pi we will get something like this. So, this will be x j omega magnitude for Fs less than 2W, this is for Fs greater than 2W. And we see that here there is some mixing between different copies of the original spectrum. So, in this part there is some mix up, and as a result it may not be possible to get, and what we get, this is actually the sum of these two components here. Here this will be the spectrum will look like this, and then something here which is the sum of these. Here this is just the magnitude. So, when we take sum, we have to take the complex numbers and then add. So, the magnitude of that will have some shape, and it may not be possible to get these values from that sum value, and as a result we may not be able to get this original signal back from this signal, because the spectrum has some mixing of the different copies of the original spectrum, and this is called aliasing. Okay. So, now suppose that the sampling frequency is greater than 2W, then how to recover the signal? That is also another question that we will try to answer later. But let us also try to see, here we have seen in frequency domain why Fs by Fs greater than 2W is required for recovery of the original signal, and why Fs less than 2W is not sufficient. It may not be possible to recover the original signal if Fs is less than 2W. We will also try to get a feel of the same thing in time domain. Okay. So, in time domain, let us just consider a sinusoidal signal for simplicity. We have a sinusoidal signal of frequency say f naught. So, this is sin 2 pi f naught t, and let us choose a frequency Fs which is less than 2 times f naught, the maximum frequency of this. What is the spectrum of this sinusoidal signal? Its spectrum is just 2 deltas. This is the magnitude spectrum, 2 deltas. So, this the signal is sometimes denoted by xt, sometimes st. So, here with the convention we are following, we take the signal to be xt, then this will be x, and this will be at f naught and this will be at minus f naught, this is 0. This is the spectrum, magnitude spectrum of the sinusoidal signal, 2 delta functions. Now, sampling frequency is less than 2 f naught. So, what does it mean in terms of the sampling period? T s is greater than 1 by 2 f naught, and that means T naught by 2. 1 by f naught is the period of this from here to here. Now, if we choose a sampling frequency less than 2 f naught, what happens in the time domain? Let us just sample this at less than this rate. Let us say that one sample falls here at the peak, this. So, say here, and then so we sample, so the T s is greater than T naught by 2, that is the half period is greater than half period. So, from here the half period is here. So, the next sample will come later than this. So, let us say somewhere here. So, this is the next sample. So, we get here a value this, and then another T s later. So, T naught by 2 is here, then later let us say here we get another sample. Then another T s which is greater than T naught by 2, this is T naught by 2 from here, and then let us say here we get another sample. These are the sample values we have got. Now, if we try to recover the signal from here, the estimate of the intermediate values will be obtained by interpolating these values. So, we can see the shape of the signal that we are likely to get. It is a signal like this. This is the signal we will get if we try to recover from this sample, and we can see that this signal is quite different from what we originally sampled. So, this has a lower frequency, for example, and what frequency we will get also can be actually inferred from the frequency domain. Let us see this what is happening here in frequency domain. We have the signal spectrum, original signal spectrum like this, f naught and minus f naught, and f s is less than 2 times f naught. 2 times f naught is here and it is less than this. So, f s is here. So, f s by 2 is somewhere here. So, this is Fs by 2. Similarly, here minus Fs by 2, and here we have minus Fs. Now, when we discretize the signal, the DTFT will look like this. We will have this shifted to multiples of Fs and then added, and of course, the frequency will be scaled so that Fs will be mapped to 2 pi. So, this 2 pi is the angular frequency actually. So, the frequency is Fs will be mapped to 1 if we normalize the frequency in DTFT. So, the spectrum will be, so this Fs by 2 will be mapped to angular frequency pi, Fs will be mapped to 2 pi, this is 0, this is minus pi, this is minus 2 pi. So, we have one copy here, the original spectrum, then this will be shifted to 2 pi. So, once this is shifted to 2 pi, we get another copy of the same thing here. This will come here and this will come here. And similarly, when this is shifted to 4 pi, we will get something here and another component later, and when this is shifted to 4 pi minus 4 pi, get one component here and another component beyond. So, this is the DTFT of the sample signal. And what is the recovered signal? If we recover the signal, again this pi will be mapped back to Fs by 2, because we know that Fs is the sampling frequency. So, we will recover it in such a way that this frequency is mapped to Fs by 2. So, this is Fs by 2. Then what we will get is this part of the spectrum. So, we will get our signal will be like this. And what will be this frequency? This frequency will be so that pi is mapped to this, then this is mapped to what? That is the frequency you will get, and that frequency will be simply Fs minus F naught. Okay. So, we see that Fs, the signal frequency that we have got after recovery of the signal is different from the original signal frequency. So, we have not recovered the signal correctly. Now, on the other hand, if we had sampled at a frequency greater than 2 F naught, then we would have got the same frequency back. We leave this as, I leave this as an exercise for the audience. Now, let us see how to reconstruct the original signal if the sampling frequency is greater than the Nyquist rate. So, the question is how to reconstruct. Reconstruct x t from x n. So, the answer, obvious answer is interpolation. That is, we have to estimate the intermediate values in some way or other from the sample values that we have. So, let us say we have a signal like this, and we have the samples at regular intervals, then we need to estimate, we have only these values, we need to estimate the intermediate values, because we want to make this again continuous time signal. So, one obvious way is to just join the values, that is join like this, join by line, straight line. We get some estimate of the intermediate values, and this is, and then we can of course to smoothen the signal we can pass it through a low pass filter, and that will be a reasonably good estimate of the original signal. Now, in general we can do interpolation by linear time invariant filters. Now, suppose we have, what we do is we have x n first. So, we have these values. Instead of considering them as values, we first convert it into a signal with delta functions of proper magnitude placed at these locations. So, this we make this a delta function, that is we take from x n we get summation n equal to minus infinity to infinity x n delta t minus n t. This is the Dirac delta function. So, this is an analog signal now, and then pass it through an analog filter, LTI filter with impulse response H t. This is the impulse response, H t is the impulse response of the filter. Then what we get here is the convolution of H t with this. Then the convolution can be taken inside the summation, and then we have x n times this convolution H t, and we know that when H t is convoluted with the shifted delta, we get a shifted copy of the H t itself. So, here we get x n h t minus n t. Okay. So, let us take some example and see what kind of signal this is, the output signal is. Let us take first a triangular impulse response. So, H t is, say this is the sampling period T s, and this is minus T s, and H t is this, this amplitude is 1. If this is H t, what we will get at the output? Let us see what we get at the output. So, at the input we have this signal, and we pass it through the filter with impulse response this. Now, when you convolve this with H t, what will happen? This H t will be placed at every delta, because convolution of this with this delta is nothing but this shifted at that position. And so, the output signal will be sum of all such shifted copies, shifted and multiplied by the amplitude of this delta function. So, from this the output will be, say this is, these are the sampling positions, and these are the values. Then H t will be placed here, that is the convolution of this delta with H t. Then convolution of this delta with H t is this. Convolution of delta here and H t will be this, just delta the H t shifted to this position after multiplying by the magnitude of this delta. So, all these deltas will be added because there is a summation here. So, after the convolution will be multiplied by this delta. Then the magnitude is 0 here. So, there is no copy of H t here, and then now once we add these triangles, what we get here is nothing but these tips added by straight line. When we add these two graphs, we get this straight line here. Similarly, we add these two, we get a straight line here. We add these two, we get a straight line here. So, this is the signal we get, and this is nothing but the simple interpolated we considered first, that is joining the sample values by straight lines. So, that interpolation can be done by using a linear time invariant filter. First, converting the discrete time signal into a pulse delta train, and then passing it through a suitable LTI filter. But this is not the only choice of the impulse response. We can change this impulse response in different ways and get different ways of interpolating the intermediate values. And what H t is the best then? What impulse response should be chosen so that we get a good recovered signal? Recovered signal should be very near the original signal. The answer is that we should take the following impulse response. Which is nothing but sync f s t minus n t s. Now, if you take this impulse response, the recovered signal is let us by our notation this is x, then x NTS sync there is no sorry, this is after shifting. So, if we do not shift it, we get simply t. Let us write it fresh. If we take the following x t, h t, the sin pi f s t by pi f s t, then we will get the original signal back. If the original signal was band limited and the sampling frequency was greater than Nyquist rate, we will see that now. So, this is nothing but sync Fs t, and then the recovered signal at the output of the filter is x hat t these are the sample values, and then the shifted impulse response. Now, consider the Fourier transform of this. So, here we have taken a particular impulse response whose shape is like this. This is Ts, this is 2 Ts, 0, minus Ts, and so on. So, if we take the Fourier transform of this, what is the Fourier transform? X hat f is, this is just constant. So, summation n equal to minus infinity to infinity x n Ts. Then the Fourier transform of this is the Fourier transform of the sink multiplied by e to the power, because there is a shift, it will be multiplied by e to the power minus j 2 pi f n Ts. And then Fourier transform of the sink is the rectangular function, which is, this is UF, one from f minus Fs by 2 to Fs by 2. This is UF. Then the Fourier transform of this is this, that is, this is also HF, the frequency response of the filter. And now, this is independent of n. So, this comes out, and what is this? This is nothing but our DTFT of the discrete time signal. And we have already discussed that if the Nyquist rate is greater than, if the sampling frequency is greater than the Nyquist rate, then the DTFT does not have any mix up of shifted components of the original frequency response. So, in the range of minus pi to pi, the frequency response, the DTFT is exactly same as the Fourier transform of the original signal. So, this is the DTFT of the xn of the sample signal, that is, this is S, this is x j omega. At what frequency? The frequency is 2 pi f Ts, which is 2 pi f by Fs, which is less than pi. So, in minus pi to pi range, this is, this gives the, this is the DTFT, and this DTFT is same as the Fourier transform of the original signal, that is x f, if f is less than Fs by 2. For f less than Fs by 2, we get this, and when we multiply this by UF, we get the same thing x f, because f is less than Fs by 2, it is in this range. So, in this range of f, this is same as x f, that is the idea. So, what we have got is the recovered signal has the same spectrum as the original signal. So, this has, of course, this DTFT has multiple copies, but then when you multiply by this, it picks up only the copy centered at 0. So, we get the original signal back. Okay. So, in other words, we get perfect reconstruction of the analog signal for Fs greater than 2W. If the sampling frequency is greater than the Nyquist rate, then this filter gives us perfect reconstruction. Now, this is also true for band limited stochastic processes. As we said, a band limited stochastic process is defined to be a stochastic process for which the power spectral density, power density spectrum is band limited. That is, it is 0 outside minus W to W. If that is satisfied, just like a band limited signal, the stochastic process x t can be expressed as in terms of the samples at n by 2W. 2W is the Nyquist rate. So, this is the sample signal, and then the h t minus n t s, which is nothing but sine 2 pi W t minus n by 2 W. Previously, we wrote 1 by 2 W as T s and 2 pi W t minus n by 2 W. So, where these are independent samples, independent random variables for a stochastic process x t. So, any band limited stochastic process x t can be expressed in this form. So, in other words, if we sample a band limited stochastic process, we can recover the sample function from the sample values. Okay. So, in this class we have discussed sampling. We have first, so what is the purpose of sampling? Its purpose is to discretize a signal in time, because there are infinite number of time instances where the analog signal has values, and we cannot store all those values if we want to discretize the signal. And so, we need to pick up samples at regular intervals, regular instances, and store the values of the samples. So, we discretize a signal in time at a rate Fs, which is 1 by Ts, where Ts is the sampling period. Fs is called the sampling frequency. So, if we have the original signal as x t, the sample signal x n is nothing but x n times Ts. The nth sample is the value of the analog signal at time n Ts. Then what is a band limited signal? We defined a band limited signal to be a signal for which the Fourier transform of the signal is 0 outside minus W to W. For some W, if this is true, then the signal is called band limited. And what is the total bandwidth of the signal? It is 2W, two-sided bandwidth. And that is also the Nyquist rate, which is that is the critical rate for sampling. If we sample the signal at greater than 2W rate, we can recover the original signal back from the sampled signal, and if we sample at less than 2W rate, we cannot recover the original signal. Then we have seen why it should be true in the frequency domain. When you discretize the signal and we take the DTFT of the signal is obtained from the original signal by shifting the spectrum of the original signal at multiples of 2 pi after scaling so that Fs is mapped to 2 pi and all the other frequencies are mapped to intermediate frequencies linearly. If Fs is mapped to 2 pi, Fs by 2 will be mapped to pi and so on. So, we first scale the frequency here and then we repeat it every 2 pi. So, that is the DTFT of the sample signal. Now, when we do this, there may be mixing of different components and that is called aliasing, and that mixing will happen if the sampling frequency is less than the Nyquist rate. And so that is not desired, because in that case we may not be able to recover what these values are from the mixer of these two copies. So, on the other hand, if there is no mixing, then we can recover this original spectrum from here, and we saw how to do it. We also saw how in time domain why Nyquist rate is necessary for recovery of the original signal, and if the original signal is greater than if the sampling rate is greater than Nyquist rate, we have also seen how to get the original signal back from the sample signal. We have seen that we need to take this this impulse response and pass the delta train obtained from the original sample signal through the filter with this impulse response. If we do pass that delta train through this impulse response, after convolution we get the original signal, because in the frequency domain we see that the spectrum of the output signal is same as the spectrum of the original signal, original analog signal. So, we reconstruct the signal perfectly from the sample signal, and this is possible because the sampling rate was chosen to be equal to or greater than 2W. Thank you.